Introducer. I love this acceptance. Okay. Good morning, everyone. Thank you so much for attending our rescheduled webinar presentation here. I'm really excited to introduce to you Dr. Qi Zhang, who is a hydrogeophysicist. Dr. Zhang studies complex fluid rock interactions using geoelectrics, nuclear magnetic resonance, and modeling tools. She's a tenure track assistant professor in the Institute of Meteorology and Geophysics at the University of Vienna. And before joining the University of Vienna, she was an assistant professor in the Department of Geology at the University of Kansas. Dr. Zhang is interested in understanding the tightly coupled physical, chemical, and biological processes that govern the behavior of geologic media and their constituent fluids from the micro to macro scale. Currently, she's working on understanding water distribution, weathering, and geochemical fluxes in carbonate rocks. So thank you so much for joining us today, and we're excited to hear your presentation.
Thank you, Blair, for the introduction, and thank you, everyone. And I'm very happy to be here to talk about my research, especially with our fellow geophysics enthusiasts. So my research is interesting and relevant, and I hope you can find some common research interest with my research, so we can maybe discuss the science all the time. So let me share my PowerPoint now. Can anyone see my screen?
Yes, I can see it.
Okay, yeah, I need to. Okay. Okay, great, thank you. Yeah, so today I'm going to talk about carbonate critical zone problem, and especially how we can use geophysical tools to look at the water distribution and partitioning in carbonate rocks. And for those who just answer your favorite geophysical method, seismic, I hope you're not going to get disappointed today, because I'm not going to talk about any of the seismic results. So I just want to give a little bit introduction about myself, which Blair already did a very nice introduction. Actually, some of my own background, I grew up in Lanzhou City in northwestern part of China, just next to the Yellow River, which is situated in the beautiful Luz Plateau. And for the past few years, I was assistant professor at University of Kansas in the middle of the US. It's also a center of very important aquifer, high plain aquifer, which extends through 8 states and is a principal source of water for this region. This is one of the major agricultural areas in the US. And currently, this aquifer is facing a serious depletion problem. And earlier this year, my research interest, also my family, took me to the beautiful Eastern Alps. So currently I'm in Vienna. And for the past few years, and my research always centered around the topics between the rock and the water interactions and how to use the geophysical tools to look at such interactions and especially apply in different environments. So I want to bring your attention to this recent study report published by NSF called A Vision for NSF Earth Sciences 2020 to 2030. In this report, they identified 12 compelling and high priority research questions, reflecting this interconnection between the different Earth systems. I think geophysics plays very important roles in answering some of these questions, such as plate tectonics, earthquake, geohazards, biogeochemical cycle, volcanism, and of course, critical zone and water cycles. And I think participants today, you probably have your own research interests and questions. For me, I'm particularly interested in the critical zone problem and the water cycles. And I'm working with geophysical tools to answer questions like how the subsurface heterogeneity influence the groundwater flow and the nutrient transport, and how to quantify such flux of water and nutrient and distribution and the partitioning of water in the unsaturated zone. And I'm also very interested in the limestone weathering process in the carbonate terrain. So if we look at this groundwater issue in a global scale, looking at this groundwater system, studies have found out about 1/3 of the Earth's largest groundwater basins are being rapidly depleted by human consumptions. A recent study shown on the left, published earlier this year in Science, and this study used 39 million wells from 40 countries from the time period 2002 to 2017. And it shows that up to 1 in 5 wells are at risk of running dry if the groundwater levels decline just a few meters. And another issue is related to the groundwater quality. So if we're looking at our day-to-day life, in all these anthropogenic activities, such as agriculture, urban industry, they all present risks for groundwater contamination. So what is special about the carbonate system? Why we want to study the carbonate system and understand the carbonates? About 15% of the ice-free terrestrial land is covered in carbonate rocks in either continued or discontinued forms. And this map is from a recent published paper, this map called the World Karst Aquifer Map, showing the global distribution of carbonate rocks that represents the potential karst aquifers. And you can see the surface exposure of the carbonate rocks occurs in all sorts of places, in plains, in hills, in the mountains, and in all range of climates, from arid to cold and to warm area. About 25%, so 1/4 of the world's population rely on the carbonate terrain for the potable water. And this demonstrates a global importance of the carbonate system. However, we do not know much about this complex carbonate aquifer, especially when we have an emergent need for very large-scale quantification for groundwater modeling. Those large-scale simulations strongly simplify the groundwater system, and there's very little understanding about such very complex carbonate aquifer subsurface. In a recent study by Hartmann et al., they quantified the rapid transport of pollutants by fast flow into the carbonate groundwater system in Europe, North America, and the Middle East. The simulated rapid, or they call it focused recharge, fractions of the groundwater recharge within one season, which is less than 19 days, sometimes can reach 77% in the Mediterranean region, and up to 50% of this infiltrating pollutants may still exist and reach to the groundwater table. So this implies the groundwater contamination risk is much larger than we expected in these fast flow carbonate regions. And if we focus on this problem in Europe, carbonate rock covers around 1/4 of Europe's land surface, and it's home to around 1/3 of its population. Especially in Austria, the country I'm currently in, carbonate covers about 20% of the land surface, but it supplies almost half of the drinking water to the entire country. And on these 2 pictures I show here is, first is the book published by several Austrian scholars to study the caves and the karst in Austria. And on the right, showing inside of a cave, Kraushöhle in Hochschwab mountain region, which is the main water supply for the city of Vienna. And this creek you can see here, this creek name is called Kleiferkühle. And this creek is one of the largest karst spring in Eastern Alps. And the discharge rate can be higher than 10,000 liters per second. So it's very fast flow. Due to the carbonate mineral dissolution by carbonic acid, the carbonate system can be viewed as a global CO2 sink. and it represents a short-term carbon sink which can impact the atmospheric CO2 concentration for a short time period. And due to its faster reaction and rapid geochemical fluxes, the carbonate system is very sensitive to the perturbations and climate change, and also very sensitive to the land use change. You probably have heard about this idea of critical zone. So the concept of critical zone is what we think is so-called the skin of the earth, which is very important, extends from the unweathered rock to the canopy, sustaining almost the entire terrestrial ecosystem. And this very reactive skin of terrestrial earth influences the moisture, groundwater, energy, and the gas exchanges between the land and atmosphere. For the carbonate terrain critical zone is dominated by the chemical weathering process, mainly dominated by these two reactions, the carbonate rock precipitation and the carbonate rock dissolution. And carbonate critical zone has a great variability in terms of water flux, sediment flux, nutrient transport, and very vulnerable to external forces, as I just mentioned. Many researchers, me included, are very interested in the architecture as well as a function of carbonate critical zone. So for the architecture, some of the common targets, including the lithology, pore structure, as well as a regular depth of the critical zone. And the main functions to be studied, including the water distribution, the flux of water, sediments, nutrient, and carbon, as well as a weathering and reaction to the perturbation process. And also, very importantly, we like to study how the architecture and function interrelated with each other. So there is a US NSF-sponsored Carbonate Critical Zone Research Coordination Network just established last year. I participated in this network and attended several of their workshops and a series of activities. There are many very great and key scientific questions identified during such events. And to separate them into a spatial and temporal scale, for spatial scale, there are important questions such as where is a base? So where is a boundary of the bottom of weather bedrock in the karst system? All questions such as how do lithology and the rock fluid interactions impact subsurface architecture? And what are the impacts of structural heterogeneity on flow and transport at different scales? And how does weathering pattern respond to climate change and land use? Similarly, on the temporal scale, several key questions also have been identified, such as what's the rate of the flux of water, CO2, sediments, and nutrients? And what is the weathering rate? And what are the time scales that are relevant to study the human impacts on the carbonate critical zone? I think all of these questions are very great questions and pose this key characteristic of the carbonate critical zones. Very fortunately, I think we have some very useful tools like geophysical methods, which can provide the opportunity to answering those questions, to remotely examine the critical zone architecture and the function over the different spatial and temporal scales. So within the critical zone research, a range of physical properties being explored by different types of geophysical methods, such as seismic, GPR, electromagnetic, NMR, electroresistivity, self-potential, gravity, and also temperature sensing, which are some of these questions I asked you earlier in the polling. And in this review paper published in 2015, and the authors have reviewed all these methods, the application in critical zone research, very, very thoroughly. But I also think for the past few years, the research has been so active, and maybe it's a time for another review paper like this. So for the geophysics application in critical zone, there's several common targets, such as to determine the depth of the regolith using geophysical methods, mainly using seismic, and to look at the hydraulic pathways, and also to look at the groundwater, surface water interactions, and also looking at the root system. And ERT as the one of the methods sensitive to the water often be used. So here I want to show you two examples. On the left, there's this is a study done by Flinching et al. 2018 in a high mountain watershed in Wyoming. And in this study, the authors identified the thickness of the saprolite, the depth to the bedrock, using the seismic velocity, and they also use the NMR to determine the water holding capacities of saprolite and a fractured rock and a fresh bedrock. And on the right-hand side, and this is a study done by Hayes et al. 2019, and this study is in Southern Sierra's critical zone observatory. And in this study, the thickness of the weathering zone of this place has been determined by the seismic velocity. And this one showing here is the PV velocity contours in the thin black lines at 1, 2, 3, 4, and 5 kilometers per second. And you can use some of the petrophysical and some rock physics model to calculate the porosity from this travel time tomography. So there's some other examples. This is a recent study done by Partitioning et al. 2021 in their recent publication in Geophysics. And they used the ERT and the seismic image to classify critical zone subsurface material into hydrophysics, a similar idea as we identify the lethal physics. So they categorize this different materials into the different phases with a relative stiffness and wetness. So they have the glacier deposits, they have granite, and also they have volcanic rocks. And on the right, this cross plot indicates the hydrophysics classification. And such categorization and classification would be very important for the further hydrological modeling. And finally, I want to show you another example done by Velos et al. 2016 in a carbonate region in southern France. And in this study, the authors show that the shallow time-lapse ERT and time-lapse seismic refraction tomography, they are correlated very well with the hydraulic data, and both the resistivity value and the velocity decrease with the increase in rainfall. And they also believe that very strong variation of the velocity is due to the dissolution of the dolostone in this region. And I want to show you another example before I jump into my own study. This example is quite relevant because this one showing not a very pure karst system. This one show in Guizhou province in China, in a long-term karst eco-hydrological observation site. This 1.2 square kilometers watershed called Chenqi watershed has a different geologic formations composing by thick limestone, dolomite, and the thin bedded limestone and the milestones. And the authors using the 3D ERT survey, combining with the temperature tracer and stable water isotopes to identify the fast and the slow dew flow regime reservoir in this watershed. And they also using the resistivity to combine with the other information to review the permeability distribution. And the low resistivity layer identified in the 3D image is believed to be the milestone layer, which is very important dominating the regional flow here. This is a horizontal continuous impeding layer and channeling the spring flow and confining the deeper groundwater flow. So as a result, most of the water stored in the hill slope is likely to flow out in the form of spring water rather than going deeper to recharge the groundwater. So with all of this in mind, I want to take you back to the mid-continent, to Kansas, and show you a case study of the middle karst hydrogeophysical investigation in Kansas region. So this is project did with my previous KU colleagues and some other colleagues, and I want to thank all my collaborators on this project. So previously, I introduced the importance of the karst region and why study the carbonate system is important. So here I want to show you a system called a mirror karst system. Unlike the hollow karst or the mature karst system, the mirror karst system is an incomplete or impure karst system. It's featured by very thin limestone limestone formation, and usually it's very shallow and has interbedded with a shale or the mudstone. And it doesn't really have the opportunity to form a large conduits or sinkholes or caves yet. You can consider it's early stage of the karstification process. And most of this mirror karst system is like layered cake, and it's mostly horizontal. And it's widely distributed worldwide, and very important to support the riparian zone ecosystem, and very important for us to understand the karst evolution. And also, as all this karst region, it's very vulnerable to the external forces. So this is the study we published last year. This is a study done in Kansas Prairie, which is a tall grass prairie and a long-term ecological research site with very low human disturbance. So this is Kansas, and this is our study region. And within this our study region, we focus on a small watershed. It's N04D here. So in this watershed, we have a very well equipped research infrastructure. We have 35 groundwater wells have been monitored over 30 years. And so we have tons of this hydroclimate data. And we also know pretty well about the groundwater level, composition, and the groundwater temperature. In this region, from such long-term monitoring, we know that this region has a very rapid groundwater surface water interaction by measuring the groundwater level and also the composition temperature change immediately after the precipitation events. And also in this region, we find out the limestone dries more often than the shale layer. So we focus on these two limestone members. One is called ice limestone, which is on the top, and the lower limestone is called a moraine limestone. And you can see from this stratigraphic information, the limestone and also the shale layer are very, very thin. So it's a very thin limestone shale, limestone interbedded system. So this is a picture when we went out to the field, and this is where we did our ERT survey, and we had some lovely guests, some bisons stop by and check out. So besides ERT, what else did we do? So we did a surface NIMR sounding and a borehole NIMR test, as well as a JPR during the dry season. And we designed the experiment in such way that we can cover the morphological control on the water distribution by looking from the upslope to the valley. We also are interested in how this water distribution along the stream. So we have this profile near the outlet and upstream in the spring. So this is probably going to be a bit busy in terms of our symbols, and I want to just point it out. And all these circles are indicating the monitoring well, and the circles colored in green indicating the borehole NIMR, and the circles colored in orange indicating where we got our core samples, and which I'm going to introduce later. So I want to show you some of the results. And here I show this two profile, P2 and P3B. P2 is this profile here, and P3B is this profile here. And this is a resistivity tomography overlaying with the borehole IMR determined water distribution data. And we can see this, this resistivity line down this two direction, the parallel or perpendicular to the stream. And this shows a very strong lateral and vertical variabilities. And this northern, the northern superficial part of the transect P3B is overlain by a cluvial clay deposit and has very low resistivity, which is here. And while this ice limestone directly below that has high resistivity value, so we call that is flip-flop resistivity pattern. And we believe such flip-flop resistivity pattern, which we also observed at other profile at this site, is an indication of weathering and vertical connectivity, especially at the secondary porosity development for the lower limestone layers. So if we take a look at the surface NMR data, the surface NMR, the one-dimensional sounding that average the information over the loop size. And here we use the loop size, which is 35 meters, while the depth of investigation for our case is about 3 meters below. And the surface NMR data review, we have the lowest water content for the middle slope profiles, and a slightly increased water content in the upslope locations. And in all those profiles, we find out there's an increased water content in the upper shale limestone boundaries. This is also very interesting, which is consistent with some previous study like this Chenqi watershed study. They also noticed this what increased the water content at the marlstone and the limestone boundary. However, due to the very long dead time of surface NMR, which is 10 milliseconds, we assume that we actually underestimate the water content because some of the water content reside in the very small pores simply cannot be captured with our instrumentation. And I also want to show you some of the borehole IMR data. This borehole IMR data we did using the DART system from Vista Clara and with 25 to 50 centimeter interval in a dry condition. And here I show the two wells, well 4-6 and well 1-6. One is at the upstream and one is on as downstream. What you can see here is the water content, which is the white line here, as well as the T2 distribution, and as also with the characteristic T2 value, which is a T2 ml value, which is shown as a green line here. So the shallowest borehole IMR data we did is confined by the depth of the well. So the shallowest one we did is the well 2-5, which is this one, and the deepest one we did is actually this one 4-6. And we can see this shale layer actually has higher water content. While the T2 distribution data showing such high water content almost entirely reside in the small pores. And we also noticed the very obvious bimodal distribution in the limestone layers, indicating the limestone layer, you have a dual flow system. So you have water residing in very large pores. You also have water residing in very small pores. And in general, we show that the borehole IMR data has shown more of the mobile water in the upstream direction, and overall we show this greater vertical connectivity than we previously thought. So these field efforts actually are quite interesting, and by combining different geophysical methods together, we show that strong lateral and vertical lithological heterogeneity do exist at our site. And especially important to point it out is the downward vertical connectivity between the limestone units, which controls the groundwater flow and can reach even deeper units. And our results also has an implication for the weathering process, especially to give some hints about the enhanced secondary porosity near the stream. Such detailed understanding of subsurface heterogeneity is very important for building the groundwater model in carbonate region. Here I show example from Hartmann et al. 2017. And in this paper, they show that in a heterogeneous recharge model, if you don't consider the heterogeneous subsurface property, and you very likely to have you're very likely to have an overall underestimation of this recharge. And in their heterogeneous subsurface model, which is scenario B here, in this they consider the variable thickness of the soil and the thickness of epikarst, also the hydraulic conductivity. So in this way, you see this heterogeneous representation fits much better with the observed data. But there's still something we don't know. What we don't know is how does the groundwater partition in the weathered bedrock in Vadal zone? And how does the rock moisture involve during the drying or the wetting period? So to come back to the basic concept, how we define this rock moisture, it was first defined by Rempe and Dietrich in their paper 2018, which they define as exchangeable water stored in the weathered bedrock beneath the soil, which is a very significant water source to vegetation and to stream flow. You're probably familiar with the concept of soil moisture. So the rock moisture is just the moisture content stored beneath the soil, but above the bedrock. So this is something we still don't know. Even some of the researchers did similar study to look at how important the rock moisture is to the vegetation, to stream flow, especially some at some time it can even buffer the external climate change. However, these questions has not been fully investigated. So we took some of the core samples from the same site, and we took them back to the lab, and we're trying to use NMR method to determine the dynamic partitioning of the rock moisture in order for us to conceptualize the critical zone function. So this result just published in the paper Geophysics by my PhD students. And as I mentioned, we took some of the core samples from this two important limestone formations, which are the important groundwater resources for that region. So the upper limestone formation, we called it the ice formation. So we have the two samples from this formation. We also have one coring sample from the lower formation, which is Morel formation. And in between, we also have the complex from this shale formation. As you probably can tell from such a thin section analysis, these core samples we selected actually shown some of the samples have very well connected pores, while some you even don't see the visible porosity. And some like the samples M2 showing here, which is the lower part of this limestone formation. And this one has very large porosity. However, those pores are isolated and filled with a cement. So we did a drying experiment. We first saturate all the samples, and then we put into a climate control chamber, and we let it dry. And during this drying process, we take the NMR measurements periodically. And on the right, you can see this is a volumetric water content change during the entire drying process. And the green line is basically showing that when you have the highest water content, basically 100% saturation, and the red curve showing when you have the lowest water content. And this is, if you're reading horizontally, this is corresponding to each of these core samples. And now in the middle, I'm showing this result from the peak decomposition analysis. The left panel here is the peak decomposition results for all the samples at fully saturated condition, so 100% saturated. And this middle panel shown is all the samples at half saturated condition, which is the 50%. And the solid line here is the actual measured T2 distribution, and all the colored dashed lines are corresponding to optimized multi-Gaussian distribution, which in this case, we picked 4 representative peaks for each of these measurements. So you can see that especially some of the samples, you can clearly separate their peaks according to their different pore environments. And here, the right panel shown here is the stacked contribution of each of such peak to the total volumetric water content at different saturation. So the most left bar showing the 100% saturation, and then we labeled the 50% saturation for different samples. So from this analysis, what you can gather is the drying process behaves differently for different samples. For some sample like this E2 sample, the water in the large pores dried first, and gradually the water in the small pores dried. However, for some samples like this M2 sample, the water residing in all sides of pores dries almost simultaneously. So this is a very interesting behavior, and it's very important for us to know during the drying period and how the water residing in the pore system actually move. So we also designed a T2 store T2 measurement, which trying to detect if there is any potential pore coupling phenomena, which means if the water actually moves between different pore systems during this drying process. To give you a little bit of background about T2 store T2 measurements, this is a measurement designed to detect the chemical shift of proton and to monitor the exchange of water among different pore environments. Here is showing that this is how the experiment sequence is being composed. Basically, you have 2 T2 experiment periods with a short storage time in between. This short storage time allows the water molecules to exchange from one pore environment to another. So how to read this information here? So this is a T2 store T2 map for sample E2 at 50% saturation stage with a storage time of 100 milliseconds. When we analyze the T2 results, the pore coupling is evidenced by the off-diagonal signals. So if all the signals are along the diagonal of this T2 map, such as this part here, and this suggests that there's no exchange among the water molecules in different environments. The mixing time is much shorter than the exchange time in the system. On the other hand, if we do observe a presence of cross-peak signals, this off-diagonal signals like this one showing here and this one showing here, this indicates we do have the exchange of magnetization during the mixing time. So these 2 square boxes here indicates a 2 pair of such water migration, and 1 pair is between the 0.1 milliseconds and a few milliseconds, and another one is between 20 milliseconds and 100 milliseconds. So what we can get from this, this study, we use this peak decomposition method to quantify the NIMR T2 spectrum and to provide some of the very first quantitative analysis of how the water partitioned during this drainage process. And we also gain some improved understanding how the unsaturated flow in the weathered bedrock, how much of this low matrix potential water we have versus versus high matrix potential water. And we also can see from our samples, some of the pores, even they're very well developed but isolated, and they have very long residence time. some of this detailed understanding for such pore structure is very necessary in order for us to determine the residence time in such system. And also our study provided some important insights into the dry season evapotranspiration system, because such water distribution or partitioning is important for some of the vegetation, and some is for the gravity-driven flow to the stream. So what we are working on this topic, so currently learning the experience from the field and from the lab, we identify some problems. And my PhD student Fan is working on how to apply this peak decomposition method to both the surface and borehole NIMR data sets. So beyond the lab NIMR results, and trying to investigate the surface and the borehole NIMR sensitivity issue, and to investigate what could be the potential errors introduced by the pool data quality collected in the field. So to summarize, I hope I gave you a very overall look of my research, and also other people's research in the topic of carbonate critical zone hydrogeophysics. I also want to point it out, it's very important to really study at different scales, not just the field scale, but we also need to go to the laboratory scale, and we also need to find a way to upgrade our results to the watershed scale. So our own research group has also done some work at laboratory scale, looking at not just the core plug measurements, but also doing some pore scale modeling, trying to simulate, for example, the precipitation and the dissolution process. And we, of course, we still hope to do a lot of the field work and trying to connect the study we find of the information we established from the laboratory to the larger scale. So with this, I still want to circle back to the remaining science questions, which I posted earlier as identified by the critical research coordination network. As you can see, I'm now going to read through all of those questions. All of these questions are still remaining science challenges. And I really hope we can use the geophysical tools to really study these questions in the context of study the water cycles, geohazards, critical zone, and biogeochemical cycles. And I hope someday we can really have a very detailed understanding of such heterogeneous carbonate system in order for us to build a more sophisticated climate critical zone models. So with this, I want to conclude my talk, and I want to thank all the attendees. And I also want to thank my mentors, mentees, and all my collaborators. Thank you.
Thank you so much. I have some questions here I want to get there on specific slides. Monika has a question about, is there a connectivity difference between the three cores that you showed on slide 26?
Okay. Yeah. Let me go back to the 26. Yes,
I'm glad she put the slide number in there.
Okay, yeah. Yes, thank you for the question. Yes, of course, we do see the connectivity difference. This is evident by both the thin section as well as the NIMR response, because you can see that as we highlight some of these pores very well developed, but they're not well connected. So you see the cement filled pores. So yeah, we do see this connectivity variance.
And then she also asked, what are the differences in sensitivity between the field and the lab NMR?
Yeah, this is a great question. If I may, I want to actually re-show some of my slides.
Absolutely.
Thank you. Yeah, we are here. Actually, I prepared some of this backup as an NIMR backup. So this is our lab equipment, which is the one I believe Monika also has, maybe slightly more advanced ones. And this is a magnetic field about 2 megahertz. And this is the other two NIMR measurements in the field I was introducing in my talk. So the boron IMR, we have a magnetic field strength about 450 kilohertz. And for the surface NIMR, depending on the different geographic locations. And for example, at Vienna, it's about 2.08 kilohertz. So you can already see that the different magnetic field strength can have an impact on this data. And in terms of sensitivity, another important thing I want to point out is the data in terms of data quality is also the dead time. As I mentioned, the surface IMR has a very long dead time, 10 milliseconds, and the borehole IMR current equipment we were using, the DART system, has slightly shorter dead time. However, it's still longer than the lab NIMR. Therefore, some of the information we can measure in the lab, we cannot measure in the field using these two, a borehole or the surface NIMR.
So which method, this is a question for me, which method, other geophysical methods, would you say is most complementary when you gather data? Like, you know, because we always need that, supplemental information. Would it be ERT that's kind of most?
Yes, actually, we rely a lot on the ERT data as well. And I was hoping that, for example, some of the studies I highlighted here is from other researchers actually also showed, for example, this one is an ERT coupled with seismic, and this one also ERT coupled with seismic, and this one is a 3D ERT measurements. I think ERT is still very powerful and very useful too, especially for this carbonate region aquifer studies. And I actually want to point it out, one of the disadvantages of our study, which is here, we didn't do any 3D ERT survey or any kind of 3D survey. However, we all know that the karst development is highly heterogeneous, and most of the structure, those characteristics, and like the karstified parts can be a 3D feature, which you easily miss from the 2D measurements. So if we ever get a chance to go back again or design a similar study, I probably want to consider some more sophisticated and comprehensive measurements.
And for this Kanza site, so if I remember correctly, you said that the shale was actually the ones with the highest water content?
Yes, exactly from this borehole IMR measurements.
So my geology brain is like, what?
I think the situation was that, remember, we went to the field during the very extended drying period. So because the limestone region, those limestone layers, which is on top and below the shale layer, has very large pores, and the residence time is quite short, and it simply cannot just hold the water for very extended long period. And then on the contrary, the shale layer in this scenario actually behave even a localized water storage part for this region, because you have a smaller pores and can hold the residence time of the water in this shale region will be much longer than the limestone ones. But if you want to do another experiment immediately after the precipitation, the results are probably going to be different.
Just like right after it was wet or something like that. No, that's really cool. I wouldn't have thought
we didn't do it. So this is my Kansas memory and the Kansas work, and I still feel very happy to see these pictures.
Yeah, they were just out there.
Yeah.
So Monika has another question. She's a little off topic perhaps, but should we expect a difference in the residence time for charged contaminants, and can we base this on the NMR T2 times?
What kind of charged contaminants we're thinking here? I think, for example, so hydrocarbons definitely have maybe not exactly a residence time in the pores, I guess. Okay.
Monika, can you type into the chat what you mean by charged contaminants?
Yeah, hopefully, but then NMR is sensitive to the water molecules, to the proton, right? So we probably cannot identify if those remaining proton is water or certain type of contaminants if we only do the T2 time distribution measurements. That's my guess, because previously we also did some lab tests for the toluene versus pure water saturated sediments. And it was very difficult to differentiate the toluene signals from the water saturated sediment signals.
Okay. And then I have one final question for you. Oh, wait, maybe did she type into here? Okay, she put in there salts, brackish water, HCs, napples, denapples.
Yeah, I think okay, yeah. I don't know. Because as an example, as I just said, toluene is one type of this NAPO, right? So we did some tests. It was very difficult to separate it from the signals of toluene saturated or not complete toluene saturated, like a 10% of toluene saturated sediments versus pure water saturated sediments. So I guess it would be difficult if we just measure the T2. However, if you have the capability of measure such 2D measurements, such as DT2 distribution or T1, T2 distribution, maybe we can see some of the evidence. For example, we definitely see, if I may, I can share this back again. So for example, we can see some of the thing like this. So this is in the lab though. This is T1, T2 map for the shell samples, and you can identify the bound region, organic pores and inorganic pores by comparing to the SEM images. So this could be possible from the T1, T2 map.
Hey, cool. And then one final question. We have a lot of students who watch our webinars. So I wanted to ask if you could give any advice in terms of coursework or, field experience, whatever it is, what would you recommend for students who want to do this kind of work?
Oh, I think, oh, that's a good question. I have to think about it.
I should have told you I was going to ask that one.
So my personal training experience might not be that straightforward. I started as an environmental scientist. So that was my major back in college. But then I started to learn the geophysical tools during my PhD time. So I guess if you have some interest in study certain problems with the geophysical tools, it's never too late to pick up. And there are a lot of classic textbooks, but also there are a lot of webinars such as this one, and some wonderful organizations such as SEG or AGU organize different talks, seminars, and lectures. And I think that probably would be a good way to get into the cutting edge research and to know some of the basics as well.
That's fantastic. Well, thank you so much. This has been a really great talk. We appreciate it and appreciate your time.
Thank you. Thanks a lot. Yeah.